All right, so today's Tech Talk, we're going to talk about powering SoCs in automotive applications and where they go. I'm Dean Gannon at MPS, and why don't you introduce yourself?
Yeah, I'm Raghunath Hardy. I'm a product marketing manager for ADAS, Automotive SoC core power products at MPS.
Okay, great. Do you want to talk a little bit about what you do at MPS?
Yeah, so basically I'm the owner of these products, these multi-phase digital controllers and driver mass products and some high current POLs that power the automotive SoC core rails. Like for example, let us say anything above 15-20 amps rails that power the SoCs. Those I make products for those
Okay.
applications.
Well, what's exciting at MPS for you?
Yeah, the exciting thing is that it is automotive, right? Automotive, and then it is very future looking. So now, if you compare to the traditional automotive versus where it is headed to, so I say the automotive industry is going through a digital transformation. So it used to be like a bunch of hundreds of small ECUs taking care of the local compute or any kind of data processing locally. But going forward, it is all going to be centralized, run by powerful SoCs. So this is going to enable the autonomous driving or big infotainment systems and all those. And with ADAS or autonomous driving, we are going to solve problems for this world. Like today, a lot of productivity is lost because of congestion, traffic congestions, and then a lot of money is lost because of accidents and stuff. And then if you go to the other developing countries, a lot of people don't have access to the public transportation or mass transportation. So that is because lack of the transportation, access to transportation is impacting their livelihood also. So in this shared economy where it is the automotive kind of when it becomes the robo taxis are enabled and all of that stuff, then it's going to change the world. It's going to change the problem of urbanization, population growth, and all of that. So being part of that, like me developing products that power the automotive SoCs, which solves these problems, that's what excites me every day to go to work and make these products, talk to customers, and all of that.
Yeah, that is exciting. Yeah. So those mega trends that you were talking about, how are those driving the need for your products?
Yeah, so like I was alluding to earlier, if you look at the automotive, the vehicle architecture today, so you see like hundreds of ECUs just taking care of the steering electronics or this, that, other thing, like very localized small ECUs. But in the future, if you are going to do the software-defined vehicles, this autonomous driving and all of these, the local ECUs are not going to deliver the computational power that is required. So it is going from distributed architecture to a centralized compute-based architecture. So that's where, so we do have MPS, we do have generations of experience serving the client compute or servers, data centers, AI compute, and all of those industries. So we do have the products, we do have the expertise, experience serving those markets, like powering those SoCs, CPUs, GPUs in the client space or server space. So we had that generations of experience, technology and products. So we are leveraging all of that and then trying to help the automotive industry. So now automotive, all these distributed architecture to a centralized compute. In the transformation, automotive will use as powerful SoCs as the client compute is using today or the servers using today. It will get there. So that kind of drives the centralized compute is what drives the need for my products. And then as a company, MPS, we have already had products and proved ourselves for multiple generations in the client and data center applications.
So how parallel are those solutions from what we've had in data centers and GPUs for many years? How closely are the architecture between what's in a ADAS system or an infotainment system, or coming in those systems?
Yeah, I mean, they are, in terms of like electrically speaking, they are pretty similar.
Okay.
Pretty similar. But automotive has an additional requirements of like an AECQ qualification and then functional safety and all of those requirements. So at core, the semiconductor process node level or at the basic architecture level, it is very similar.
How about for, let's say, performance demands? Are they similar?
Yeah, yes.
Okay.
Yeah, the SoCs, especially the core rails,
Mhm.
the requirements like efficiency, transient performance,
Mhm.
and all of those are pretty similar to
Okay.
the client space or
Okay.
the server space.
So how long have we been delivering solutions that are used in data centers that are the same, that are going to be used in these systems?
It's well over like 5 or 6 generations already. We
Right.
have been supporting and pretty good market share there as well.
Mhm.
So we are pretty. I would say, especially in client space, we are the dominant player. Just because we do have the technology that those products that solves customers' problems in that space. So
Yeah.
that's why we are enjoying that market share.
Do you want to maybe go into a little bit of detail about what those, like maybe a couple handful of problems that we've solved over time that will work well in this for this application?
Yeah, sure. The traditional ways of doing implementing this SoC core power is that there is a controller, there are discrete components like couple of FETs, and then for current sensing, there is a DCR way of doing the current sense, and then the temperature sensing, and all of this is done in a very discrete way. So it takes a lot of components, and then it takes a lot of effort from the designer to design with so many components. But and also another thing is that the controller was an analog controller. So where if you have any changes to make, then the designer has to go change the components, redesign everything or optimize it. But the MPS, how we approached it was, we made digital controllers. So these have MTPs, so where you can read and write them multiple times. So these are digital controllers, and they are multi-phase. So that's on the controller side. And then for the power stage, instead of using high side FET, low side FET, external current sensing and all of that, so we came up with the Monolithic driver MOS technology. So everything is integrated. In that power stage, you get both the FETs on there, and then the current sensing and temperature sensing is all done, and then all kinds of protection features all implemented on a single piece of silicon. So from design standpoint, it is very easy to design them, very easy to scale up or down, and it speeds up the design cycles, very flexible, very scalable solutions, and very efficient as well. So since these are monolithic driver MOS, everything is on a single piece of silicon, so we can really optimize them and get the highest efficiency and fast transient response as well.
Yeah, so that's the benefit of having 5 generations of this product, where you're integrating all of those into, you keep finding different things that you can pull in, different
Right.
functions, right?
Exactly. Yeah.
Can you talk about the benefits customers see by having the digital product versus having, say, a more traditional analog solution? So
Yeah.
whether it's design, startup, production, any of those phases.
Yeah. Yeah, so like I was explaining earlier, our products, since they are digital, so they are so flexible. So if the designer has to change anything, he doesn't have to go physically change a resistor or a capacitor. So we offer so many the register settings. So, and we have during the development process, we have a GUI that the customer can hook it up to a PC, and then while if he needs to optimize something, tweak something, just he needs to go to the GUI and then change a couple of register settings, and it is done.
Can you have like a specific thing that they're trying to optimize for or change that you've come across that?
Yeah, for example, like, if the designer is looking for a sweet spot, frequency versus efficiency, let us say.
Okay.
So the frequency, we can change through a GUI,
Mhm.
and then take a measurement of efficiency. And then the another piece is the transient response. These are all kind of interlinked. If you change something, then something else will change. But if it is done the traditional way, then it is a lot of work to change the components and all of that. So as opposed to that, we can change the register settings and then take a measurement there and then change it again and take another measurement. And then you get all this data and then you compare and then you find your sweet spot of best efficiency, best transient response at the desired frequency.
And even some of the software, there are some automated, I think, profiles or automated ways of testing these types of situations.
Yeah,
Like,
it's possible.
So you can have the system actually check all of these, a lot of parameters, and see what the responses are too.
Absolutely. Yeah, actually, you bring up a good point, Dean. So these are digital controllers. They are real time. The controller, driver mouse together, they are monitoring all sorts of things like the cycle by cycle current sensing and temperature sensing and all of that. And then the controller is always talking to the system CPU or SoC. So they get the real-time monitoring, and then real-time, like if anything has to change on the fly, they can implement that too.
Yeah,
Yeah.
yeah, that's an amazing solution.
Yeah.
How about you? Can you explain what differentiates our products from the solutions that are available now on the market?
Yeah, the differentiation is our digital controllers, multi-phase digital controllers, having that flexibility as I was explaining earlier.
Yeah.
And then the driver mouse being a monolithic driver mouse. You can get the smallest package size, which lends itself to a small solution size. Like the PCB real estate is a premium in any application, and it applies to the automotive applications as well. So our driver mouse can save driver mouse, and then our performance, like transient performance. Our technology can enable to use fewer output capacitors. So that overall saves, cuts down the. Let us say we have done competitive analysis in some cases where we saw up to 50% savings in number of components versus the traditional solutions, and up to 20% PCB size reduction using our products compared to traditional solutions.
When a customer is going to actually start a design process and start working on, what kind of support is your team able to offer in these types of, they're very complicated systems.
Absolutely. Yeah, so MPS as a company, automotive, we have global presence. So we have design teams, application teams, and other support quality and other support structure all over the world. And then we do have EMC labs to help customers scan their boards to solve their EMI problems. And also, we have dedicated functional safety teams as well. So we can look at we can create safety manuals, DFMEA reports for our products. Not only that, but our expertise is so good. We have functional safety engineers coming from OEMs and tier ones that we have on our team now. They can help review at a system level, also make sure all that ASIL-D functional safety compliance is there. So that kind of support we have. So apps support global locations to support the customers locally there, and then EMC labs, and then dedicated resources on helping customers with the functional safety related topics. This is the kind of overall support we provide to the customers.
How about with the digital configuration? So we're talking about where they're optimizing or trying to tune their system, maybe some startup. There's startup boards, there's always, can be things.
Yeah, oh, yeah, absolutely, yeah. So we have, we support all the EVBs, reference designs, and all of that work, and especially for my products. So these are kind of, they require a lot of collaboration with the customers. So we kind of, give them EVBs. So we collect customers' specifications, and then we build an EVB, kind of customize that EVB for that particular customer's application. And then we'll get them started that way. And then as we are progressing along the design cycle, we can help them fine-tune their design to get them the best performance, right? That's the sweet spot. And then we can help them come up with that, the register settings and all of that to deliver that best performance. And then for every customer, we create a unique part number, because every customer's application requirements or board designs are different. So we create very specific, customer-specific part numbers, and then we take it to production.
One of the, as you're talking about that, the benefits that we've seen with the digital aspect is the ability to tune the configuration as the product goes through different, from prototyping, because things are different as they go, maybe the first, their first production runs, their pilot production runs. How does that help with having digital flexibility?
Yeah, so having digital controllers versus analog, that customers can change their design aspects very easily, and then they can fine tune them relatively easily.
Can you talk about some of the, are we just starting out in this space, or what's our experience in actual automotive applications?
Oh no, Dean. So like I was mentioning, in consumer and enterprise space, we have proved ourselves already over multiple generations. But in automotive also, we are not starting up just now. Like we have been in production for more than 3 years. We shipped millions of parts already, and they have been proven out at the customers in the field already. So this is not a startup. We do have experience in automotive space as well, in production environment. Yeah.
Do you have any other maybe success stories that you want to?
Yeah, we have been on on a major, like we have engagements at all level. For example, like automotive SoCs, the SoC makers, we are on the reference designs already, some of them, and then some of them we are working with them now. And we have been with some startup EV companies. We are helping them on their SoC power needs. And then we are well-established OEMs and Tier 1s also. So in all these areas, we are in production with some customers already, and we will be going into production soon at some other customers. And on the other customers, like we are working on their future needs and stuff, which is kind of developing the next generation of products.
Do you want to talk maybe about some things that are in the pipeline or in roadmap that you can share?
Yeah, sure. So the automotive SoC is every generation it is getting more and more powerful. Like for example, it used to be like 50, 100 tops SoCs in the past, but now look at I have seen some customers using 2,000 tops of computational power in their vehicles. So the automotive SoCs are getting more powerful. That means they need more current. So we do have products in production already, but at the same time, I'm engaging with the customers to develop some new products. Like for example, if you look at the digital controllers.
Like what's some of the, let's say some of the top power demands or requirements that you're seeing in SoCs that we're currently delivering?
Yeah, currently, I mean, we have seen like, it used to be like, sub 100 amps, but now, we are seeing something like, more than 200, 300 amps.
Mm-hmm.
So for
at what voltage?
That's at sub 1 volts, like 0.7, 0.8 volts.
Mm-hmm.
But yeah, so it's like, look at the change in last 3-4 years.
Yeah, what was the change? Now we're at 100, 200 amp, but 0.7, what was it a couple of years ago?
A couple of years ago, it probably at 50 amps, that range.
Okay.
At one application, like, I can give you a little bit more color to this. At one application, it used to be like 60 amps and stuff.
Mm-hmm.
Now that application is going to 150 amps, like 3x,
Mm-hmm.
3x, right?
Mhm.
So yeah, it is kind of taking off the SoC.
And how many generations or how many years was it from that application from 50 to 1,
Yeah,
or 60 to 150?
that just within 2 years, like just one gen to next gen.
Yeah.
Yeah.
What is what's your intuition on where they're going? The doubling every couple of years, or?
Yeah, that I'm not sure. That's a good question. But in automotive space, unlike the client space, I'm not sure about the trend, if it will double every year or
Yeah.
not. But one thing is for sure, it is like I mentioned, that 50 amps going to 150 amps.
Mhm.
That kind of trend we are seeing for sure, and
Yeah.
it will continue to grow that way.
Yeah.
So for that to serve, to go hand in hand with the customer needs, I'm developing new products for the controllers and new products for driver MOS to cover all their today's needs and then future needs as well.
Are there any other topics or concepts that you'd like to share?
So for example, there is another trend that is happening. Like today, I was reading an article. So today the 12-volt battery in the car,
Mhm.
just say I'm just rough numbers. So the 12-volt battery can supply, let us say, 3 kilowatts today. But that 12-volt battery is running out of juice because the SoC is coming up for ADAS or infotainment. The power needs are growing in the vehicle.
Mhm.
So the 12-volt battery is maxing out. So one trend that we are going to see in the future is the customers will, or the car makers or OEMs will use a 48-volt battery.
Mhm.
So that opens up another avenue for us to go develop new products to solve that problem. So today the automotive industries and the supplier base, all the components and everything is well established for a 12-volt battery. But 48 volts, it will come. In my opinion, it will come. So now that gives MPS as an opportunity to kind of jump in on that trend and then start developing new products. So from my product line side also, we are looking into some of those opportunities.
Okay.
Talking to some customers already, and let's see where it takes us.
Okay, great. Well, thank you very much for your time today. It was great to get into details about how MPS is addressing automotive SoC power needs, and thanks.
Yeah, thank you very much, Dean. Thanks for nice talking to you.
Yeah.